me say a little bit more about IR spectroscopy. So there are some more complex vibrational modes than we looked at in the first lecture. So if we had a simple unit like this, a carbon with four bonds, then you have what are known as, so if we just look at the CH, so a CH2 and an sp3 hybridized carbon, you have what's known as a symmetric stretch, where we're stretching these two hydrogens that way, and then the carbon is moving this way. Then that occurs at 2853 inverse centimeters. Or the asymmetric stretch, which would look like this. That's at 2926 centimeters. The end plane bending or scissoring mode. So these two hydrogens are bending this way, and this carbon's being displaced downward. So that would absorb IR radiation at 1465 inverse centimeters. You have what's known as a Wagang mode. So this circle with a negative in it means that it's moving behind the page, and the circle with a positive means that atom is moving out of the page towards you. So that Wagang mode's at 1350 to 1150 inverse centimeters. You have this twisting mode, 13. So these are in the same region, 1350 to 1150 inverse centimeters, and you have this rocking mode. So for the simple CH2 units, you have all of those different vibrational modes. And if you notice, 4 of these modes are down in the fingerprint region. So again, that region can be very complex because of all of these bending modes that are in them. Okay, so what's the origin of this 3n-5 and 3n-6 vibrational modes? All right, so any atom can have three degrees of freedom relative to a Cartesian coordinate system necessary to describe its position relative to other atoms in the molecule. So for a nonlinear molecule, 3 degrees of freedom are associated with rotation of the molecule. So actually rotating the molecule in 3 dimensions. So it could rotate, right, you could rotate it around the z-axis, the x-axis, or the y-axis. So that would consume 3 of the degrees of freedom. 3 degrees of freedom are ascribed to translocation of the molecule. So actually moving the molecule, it can move in the x direction, the z direction, or the y direction. So that gives you 3n minus 3 for rotation, minus 3 for rotation. So 3n minus 6 is what's left over for the vibrational modes. So, right, so the 6 are consumed by those rotations and translations. Okay, so for the linear molecule, so if we had a linear molecule, ABC, for example, so there's only 2 degrees of freedom needed to describe the rotation. That's right, because if it rotated around the x-axis, there's no change. But if it rotated around the y-axis or the z-axis, then that would change where all of the atoms are in space. So you only need 2 degrees of freedom for rotation, but you still need 3 degrees of freedom for translocation, because you could still move that molecule y along the x or along the z-axis. So if it's a linear molecule, 3n minus 5 is what's left over for the vibrational modes. Okay, so you often don't see all of the peaks or signals that you could see. There could be more, or most usually there's less for a number of reasons. So it's these reasons. So one, the wavelength where that vibrational mode occurs at simply may be out of the region that you're scanning. So if your instrument is only set to scan from 4,000 to 400 wave number, you're not going to see it if it falls out of that region, obviously. The absorption may be too weak to observe. So if the bond is not very polar, right? So we looked at an example last time. So if you had some alkyne like that, it's not a very polar bond. It's going to give a very weak signal, and you may not observe it. It may just be lost in the noise. Or if the absorption doesn't give a change in the dipole moment, then that will not be IR active. It may be that the absorptions are so close in energy that those peaks just coalesce into one, and you only see one signal. If you had a better instrument, which would give you better resolution, then maybe you could see more of those signals. Or you may have signals that are degenerate. They occur at the same energy, and so then obviously those would only show up as one signal. Okay, so it is possible that you can observe more peaks than you should be able to see, and that would often be the case due to what's known as overtone bands. So this would be absorption of energy leading to a doubly excited state. So it's going to occur at approximately twice the energy of the normal mode. So if you have the OH stretching of water, for example, and if you doubled the frequency of that, then that would be what's known as an overtone. And that's going to be at about twice the energy over where the normal band would be at. Okay, so you can approximate the energy. So if you had a molecule, you could calculate what the spectrum should look like. You can approximate it, what the stretching motion should look like using Hooke's law from physics. So in this case, you treat atoms attached to each other as a simple harmonic oscillator, where you basically have two masses. So that would be the two atoms attached to each other, and the bond would be basically represented as a spring. And so this spring force constant from Hooke's law would be related to the strength of the bond. So if we looked at an example, so XY bonded to each other, and so if we looked at how to calculate the energy required to stretch that bond, so the wave number where this would occur at is equal to 1 over 2 pi c, where c is the speed of light, times the square root of the force constant F, so the force constant in units of dyne per centimeter, divided by, so mx and my would be not the molar masses, but the masses of one single atom of X and one single atom of Y. Okay, so for single bonds, the force constant's around 5 times 10 to the 5th dyne per centimeter. For a double bond, about twice that, 10 times 10 to the 5th dyne per centimeter, and triple bonds about 3 times that, about 15 times 10 to the 5 dyne per centimeter. So if we do this calculation for a CH bond, for example, so 1 divided by 2 pi, plug in the speed of light. So speed of light is 2.998 times 10 to the 8 meters per second. So here I've converted to centimeters per second. And then the square root. So plug in the force constant for a single bond, and then a conversion factor to get all of our units to the same unit. So a dyne is the same thing as gram centimeters per second squared. And then plug in the mass for atom of carbon and the mass for an atom of hydrogen. Multiply those both together, and then on the bottom add them together. So if you do that calculation, you should get 3019 inverse centimeters is where the CH stretch should occur at an IR spectra. So the actual value is around 2900 to 2850 to 2960 inverse centimeter. And so what's important to recognize, of course, is that the CH bonds is going to be affected by whatever else is in the molecule, right? What's on the adjacent carbons or whatever it's close to in space is going to have some influence over the strength of a bond. But the basic point is, so another significance of this is, so you can do an IR spectrum and you can use where a signal is at to calculate the force constant for a bond. And that has utility then, because you could then tabulate all of these force constants for different bonds and based on what their environment is. And you can tabulate that and you can put it into molecular modeling software. So if you've ever done any computational chemistry, maybe on Gaussian or Spartan, for example, which is some of the software that we have here. So if you do computational chemistry, there's what are known as different levels of theory. You have molecular mechanics levels of theory, semi-empirical, ab initio. So ab initio is using quantum mechanics to calculate relative energies and stabilities of different molecules and different conformations of molecules. Molecular mechanics, however, is basically treating atoms like spheres and bonds like springs, so it's using some components of like Hooke's law. So if you did IR spectroscopy for different molecules and you figured out where bonds are at and figured out force constants from that, then you can put that into software that you could use to do molecular mechanics on new molecules using force constants for similar molecules. So that allows you to, and they're not very intensive calculations, so you can do molecular mechanics calculations on huge molecules like proteins. If you want to use quantum mechanics, these higher levels of theory, then of course those calculations are much more intense and you're typically limited to much smaller molecules because you're using quantum mechanics to solve what energies of different conformations of molecules are. Okay, so just as an application of this, so which bond should require more energy to stretch, a CH bond or a CD bond? So if you remember, what is D? D is deuterium, it's just an isotope of hydrogen. So when we say hydrogen, typically we're talking about H1, right? One proton, no neutron in the nucleus. H2, one proton, one neutron in the nucleus is deuterium. So deuterium, of course, has an extra neutron, so it has more mass than a hydrogen atom does. So which one should absorb at a higher wave number? That would be, since the mass is in the denominator of this calculation, right? The smaller the mass, the higher the wave number. Of course, the bigger the force constant, the higher the wave number, but the force constant for CH and CD is pretty similar. So the main effect here is going to be based on the masses of them. So if you looked at the IR spectrum of chloroform versus deuterated chloroform, for example. So the red spectrum is chloroform. So you can see that the CH bond is at a higher wave number than the CD bond. Since deuterium has a higher mass, it's going to absorb at a lower wave number. And you see the same thing in the bending modes. So if you look at the chlorine, carbon, hydrogen, chlorine, carbon, deuterium bending mode, the CL-CH bending mode's at 219 inverse centimeters, whereas the CL-CD bending mode's at 912 inverse centimeters. Okay, so that's basically all that I wanted to say about IR spectroscopy.